Uh, I hope that the screen is visible and I am audible to everybody.
Yes, sir.
Okay, so let us begin the 12th and last live session of the course Fundamentals of Manufacturing Processes, which is being offered by Professor D.K. Dwivedi of IIT Roorkee. As in for myself, I am Abhik Deb, a PhD scholar in the Department of Mechanical Engineering at ISC Bangalore, and today we shall be discussing on the concepts related to it will be a continuation of the heat treatment process and an introduction to the surface engineering process. So at any point of time, if there is any doubt, you can interrupt and ask so that we can clear the doubt right then and there. So without further delay, let us begin today's session. So the first
Sir,
question, yes, yes, exactly, yeah,
I have a doubt in the casting session. Can I ask
yeah. In which session?
casting?
Hello.
I mean, from the taper elements, applying the taper elements.
Okay, okay, yeah. Please go ahead.
So in the when we are applying the taper elements, if we are having a rectangle cube, I mean a square cube box, then
Hmm.
we will be applying the taper elements outside of the uh, uh, cube, or we will be tapering into the cube pattern.
So you were saying that suppose we are making a section like this, right? This is what you were saying, right?
Yes, sir. So
Yeah. Yes, yes.
I will post the question in the chat box.
Uh,
So the sides of the
so determine the
sides
dimension.
of the rectangle is actually.
Okay, sides of the rectangle are shown. Determine the dimension of the pattern for casting shown in the figure. Shrinkage allowance is 20 millimeters per per meter, and machining allowance on all the surfaces and board is 1 millimeter and 0.75 millimeter, and 1 degree draft allowance for external and internal dimensions respectively. So we have to determine the pattern of the casting. So what are you asking again?
So here we have the dimension here, and actually I need to apply that taper allowance to this uh, pattern. So I was confused that how to whether we will be applying it to the, if the height is actually 150 and base width is 200 and 150 rectangle.
Okay, so this
So
is
if we are
200.
taking that from that 200, then we will be tapering outside. Yes, sir.
Yeah, so this is 200, right? And the height is 150, right? So you were saying that we should
Yes,
give
sir.
the taper like this or like this. This is what you were asking, right?
Yes, sir. If you are tapering into the box, or we are tapering outside to the box.
No, we have to taper like this. That is a tapered
I mean,
structure
if the
should
final
look like
if you
this. That is a cavity. The cavity should look like this. Okay, so that the reason for this is so that when you move it out, there is an increasing clearance in this direction. If you make the tapered cavity like this, sorry, just a minute, like this, supposedly, like this. If you give the tapered in such a way that the cavity ultimately becomes like this,
so
then
I was not meant by this. I mean, we will be reducing.
you meant.
Uh, I mean, in the second figure, actually, I mean for the first figure also. But in the first figure, if we are considering the top of that trapezium, it will be 200 plus. If the allowance is 2 in that direction, 2 will be added in the both sides, isn't it? Or
Yeah,
whether
yeah.
we'll be doing it like that, or we'll be subtracting 2 from the bottom and reducing.
Okay, so you were saying that will it become. Wait,
So,
just a minute. So you were saying this is the original structure, and should you make it like this or should you make it like this? This is what you were asking, right?
yes, sir. Yes, sir.
So see,
Yes,
if
sir.
if you are providing the uh, since you will be making the pattern on this, and resulting from the pattern you will get the casting cavity, right?
So your voice is actually blurring.
Uh, Wait. Is it better now?
Yes, sir. Now it's okay.
Okay, so what I am saying is that see, you will provide the allowance, whatever allowance, the draft allowance on the pattern, such that depending on the draft allowance of the pattern, the casting cavity shape will be determined. So, if you put the pattern in this way, like this one, that is, you are reducing the bottom dimension. Okay, then the casting dimension will also reduce. Okay, casting cavity will be of this shape, right? Then if we had required a casting of this size, then the overall size of the casting is also reducing. But if we make the pattern of this shape, that is extended at the top, okay, that is a draft at the top surface like this. Okay, that is, this is the original dimension that we need, and the draft is given on the top surface, then the casting cavity will take this shape. Okay, and now when the original casting is of this shape and size, then it will be facilitating the removal. So yes, the draft has to be provided on the top surface. If we provide at a bottom surface, then we are by default reducing the dimension of the casting itself. Okay.
Okay, sir. So here we will be only applying that vertical sides only.
Yeah,
We
or
draft will be only applied.
draft allowance is always on the vertical sides only, because when we move it out, then only, like, there is a chance that it will get tapered, or the it will not facilitate the easy removal. That is why we need the tapered allowance on the vertical surfaces.
So actually, there is an cylindrical cavity inside the that cube also,
Okay.
which is given as about 60 in diameter. So
Okay.
if we are doing giving the taper allowance to inside cavities, then
Now then
how
it
we
will
will be
has to be
giving?
opposite
I
of
mean,
this.
whether we
It has to be opposite. Suppose you have to take out the code in this case, right? Not the casting. So if you have to take out the code, then you have to provide the you have to reduce, increase the dimension of the. You have to give the draft allowance in such a way that the dimension of the internal cavity increases. That's what I am saying. The main aim of the draft allowance is always such that it provides easy removal of the pattern, in this case the pattern from the casting, from the after making the cavity, and when there is a core, then the easy removal of the core. So if there is has to be a easy removal of the core, then the dimension should be extended than what we otherwise it would have been. So like if it is a cylindrical, then we have to give the draft allowance in such a way. So the draft allowance they have asked to give in the internal dimensions also. Acha, 1 degree draft allowance for external and internal dimensions. Okay, then in that case, for internal dimensions, you have to increase the draft allowance in a way such that
So the by meaning okay, sir, please.
yeah, what I am saying is that suppose this is the cube and this is the cylinder, then you have to take out the core from the cylinder inside, right? To facilitate the removal of the core, then the draft should be inclined like this. That is, the cavity should be enlarged in this way so that the core can be taken out. So you have to design it accordingly.
So the larger diameter will be at the top, similar to the here also, outside also.
Yeah, that's what I think. If you have any further doubt regarding the question, because the code, if it can be where is the code placed, the cylinder, where is it placed?
So actually you have drawn like the cube 200 and 150 height. So the cylinder will be passing throughout the that rectangle box.
Okay, so
So
see,
I have
sir,
confused
this is
whether
a
we need to
cylindrical box,
in taper in
right?
the.
This
I
is
mean,
a cylindrical box, right?
exactly.
Here, like in this section, it will be completely
It will be inside of the. Yes, sir.
inside. Yeah, like this. So like this.
It will be positioned inside. Okay.
Yeah. So what I am
Yes,
saying
sir.
is
Yes.
that depending on from which direction you are removing the core, you have to give the draft allowance in that direction. If you are removing the core from this direction, then the draft allowance should be given in this side. If you are removing the core from this side, then the draft allowance should be given in this side. That's what I am saying. So, is this a question in the assignment?
No, sir. I think it was from another question, not from this one. This year's.
From this year's?
Not from this year. It was actually I got this question from another PMR section. If
Okay,
I
okay.
didn't understand
So
that
that's what I am telling, that this needs to be clarified which direction it has to be removed. Okay, like the pattern is always removed from the top side, so you have to give the draft allowance like this. Okay, the pattern it will be removed from this side, so the draft allowance will always be given like this so that it can be easily removed. However, since this cylinder, like the core can be removed, if it is a through hole, then it can be removed from the top as well as from the bottom. So you have to be like certain first which from which direction the core has to be removed. Only then we can be 100% certain that the draft allowance is to be provided in that. Okay.
so if you are providing the draft elements like this, we will be having the same issue as that of the before. I mean, if you are giving inside cavity bigger, then there will be some portion inside that to be chipped off, isn't it? I mean, we
See,
need to remove through
see,
the machine, isn't it? If we
supposedly
do
this
it
is
like the
the
outside portion.
supposedly this is the
So
mm, yeah. Go
So,
ahead.
1 minute. If we are giving the taper, I mean, if the diameter is actually 80, if we need the diameter as 80 mm. So we will take the top circle as 80 and we'll be tapering, reducing to the bottom, or we will be taking the bottom circle as 80 and tapering it outward.
That's what I'm saying. That suppose this is the hole of 80 mm diameter throughout. Okay. This is the throughout hole. Okay. So now if the code that will be used for making this hole, if supposedly you have to take this code out, okay, you have to take this code out, right? You cannot keep the code here. So if the code is being taken out from the top, if you are designing it such that the code will be taken out from the top, then the draft will be provided like this, that is at the top surface. If the code is taken out from the bottom because it is hollow, so the code can be taken out from the bottom as well. In that case, the draft will have to be provided like this to facilitate the removal. That's what I'm saying. So you have to know, or you have to make an assumption that from which direction the code is to be taken out.
So if we are taking out from the top, then the top will be having more diameter,
Yes,
and
yes,
at the
because if
bottom
you
we will be
don't
having the
increase,
exact dimension.
yeah, exact dimension, because if you do not increase the dimension of the top, then due to when we are moving it, there will be resistance to the movement of the code as it is moved out. That is why it has to be tapered.
Okay, so here the when we also need to give that shrinkage events also. So for the internal cavity, we will be reducing the the shrinkage allowance, isn't it?
For shrinkage allowance, you have to
Inside
uh,
cavities.
inside the cavities you have to increase the dimensions. That is, if the cavity was supposed to be like this, then with the shrinkage cavity it will be like this. Why? Because it will shrink in this direction, so that after shrinkage this line, this region becomes this region. Okay.
Okay, so actually we will be reducing the side, isn't it?
Yeah,
At the
yeah,
outside
we
we
have
will
to,
be
outside we
giving
have to
more.
increase like this. Outside we have to increase the dimension, and inside we have to, the diameter we have to reduce. Yeah, diameter we have to reduce.
Okay, so when we are giving that allowance, how we will be giving? I mean, first you will, the taper allowance will be given last. In your previous lecture, an order was given, isn't it? So taper and this shrinkage allowance was given at the same time. So we will be giving the first we will give the
First
taper
you will give
allowance,
the
then
shrinkage allowance,
shrinkage
then
allowance, then we will give the taper allowance.
tapered allowance.
In
Yes.
in in which order we will be giving this taper and shrinkage?
And that's what I'm saying, that first you will have to give the shrinkage allowance, then only you will give the tapered allowance, because tapered allowance will be coming from the ultimate dimension. Okay, so tapered allowance is related to the ultimate dimension of the object, irrespective of whatever allowance you are giving or not. So before you will give, first you will give the shrinkage allowance, before, like before the tapered allowance you will give the shrinkage allowance and then the tapered allowance.
Okay, sir. The machining allowance will be given at the exactly at the last.
Yes, the machining allowance will be given at the end.
Okay, sir. Thank you, sir. So
Yeah.
one more thing. Actually, the shrinkage allowance will be given to both the solid shrinkage and liquid shrinkage. Will it be included? I mean, the allowance that given to the pattern. Will it include liquid shrinkage and also the solid shrinkage, or whether only the solid shrinkage?
See, there is a difference, right? Whatever the pattern is taking care of and whatever the riser is taking care of, right? So after, during the solid, after the solidification happens, whatever shrinkage happens, that is taken care of by the riser. So during solidification and in the liquid stage, whatever shrinkage has taken place, that is taken care of by the pattern. So do you have to consider which part of the shrinkage you are considering?
So first we will be having that liquefaction shrinkage, then we will be having
So
liquid shrinkage,
liquid,
and
no,
then
no, liquid.
we will have that solid shrinkage.
First we have the liquid to solid, liquid to the solidification temperature shrinkage, like this liquid line to the solidification
Solid.
temperature. Then there will be solidification, this entire, there will be no This is a phase change, the solidification. So the entire thing is this, and then there is a solid shrinkage. So solid shrinkage is being taken care of by
solid shrinkage.
which one takes care of the solid shrinkage?
This solid shrinkage will be taken care of by
By
pattern. So I was having this doubt that there is a liquid shrinkage during that phase change, isn't it? So will this pattern include that
yeah, 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 yeah,
both
yeah.
this thing? And in some books they are giving like it only the pattern will be taking care of the solid, and in some other place they are saying like it will include both the solid and both this liquid shrinkage, not the slanted part. I mean the latent heat part and that solid shrinkage.
Latent heat part and the solid shrinkage. But as per was as whatever I have known and whatever has been taught in this lecture, the the till the solidification from liquid till the solidification is complete is one, and after during the solid, the that is during whenever it has completely solidified, that shrinkage is separate. Okay.
So can you mark that portion that you have said in that diagram? I mean, the last part was from S to bottom line, isn't it?
Yeah. So see, this is solid. This is a solidification line. Okay. And this is solid to say the room temperature. Okay. So this is one part and this is one other part.
Okay, sir. So,
So yeah,
by this diagram, the pattern will be including only the last part, second portion, or will it include that latent heat? So it does not include that latent heat part pattern. It will be taken care by the riser only. I mean, L2S and
this
S2S.
entire thing will be taken care of by the riser, and when the it has completely solidified from solid to the room temperature, whatever shrinkage happens, that will be taken care of by the shrinkage allowance. Okay.
Will taken as pattern.
Yeah, pattern, that is shrinkage, not pattern, the shrinkage allowance of the pattern, that is shrinkage allowance given to the pattern.
Okay, so
Is it clear to you?
that S2S part is it. So that part is actually called a liquid shrinkage, isn't it? S2S.
S2S, this is the solidification region. Liquefaction, I am not understanding what you were trying to say in that. You see, different term, different books will have different terms. Okay, this is basically the phase change. During phase change, if there is any change in the volume, like from liquid to solid, there is a change in the volume, right? So that is the solidification shrinkage. That is the solidification shrinkage. Okay, that is during the solidification, whatever happens.
Okay, sir. And actually, the by meaning the total shrinkage means L2R, isn't it?
L2R,
Total shrinkage.
total shrinkage is L to this room temperature. Yes,
L2R.
yes.
And if the shrinkage allowance will be only given to the S2R, that part will
Yeah,
be confirmed.
yeah, 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 yeah.
Okay, sir.
So that's what I
So,
know, and that's what
so
has been taught
actually,
in. Yeah, please go ahead.
okay, sir. Actually, I was having this question like shrinkage allowance on the pattern will be provided to take care of. The option is like liquid shrinkage, solid shrinkage, liquid and solid shrinkage, any one of the liquid or solid shrinkage. And
It
they
will
were
be
given
only
the
solid
answer like
shrinkage.
shrinkage allowance to the pattern is provided to take care of both
Shrinkage
liquid and
allowance
solid
is
shrinkage.
is given as both liquid and solid shrinkage. That's what you are
So
saying.
I didn't understand.
What is the question?
The question is shrinkage elements of the pattern is provided to take care of. Then they are giving option like liquid shrinkage, solid shrinkage. Option B, option C as liquid and solid shrinkage.
Hmm.
Then the option D is anyone liquid or solid shrinkage. And the solution they have given is like shrinkage elements on the pattern is provided to take care of both liquid and solid shrinkage. So can we take this solution as wrong?
Yeah, see, as far as whatever I know, I think that only the solid shrinkage is being taken care of by the shrinkage allowance. Okay, it might so happen that some books might have considered ki during when the solidification starts, that is the liquid has started to solidify, that is it is in a mushy zone, right? It is like a what I can say, partly liquid partly solid, a mushy kind of structure. In that case, they might consider that it has already taken a shape of the solid, like a semi solid kind of thing, and it has the shrinkage is being taken care of by, that is the solid shrinkage is shrinkage allowance is taking care of the entire thing. But whatever I think is from the this solid temperature line to the room temperature is being taken care of by the shrinkage allowance. I think that since you have a doubt and it is a genuine doubt, I think you should pose this doubt in the discussion forum so that the professor can help you out. Okay, so like there might be some
Okay,
different
okay.
uh,
So
uh,
one more thing, it was actually a question asked in the gate 1999. I mean,
so so this is the answer that they have given, like which answer they have like from where are you getting this answer, like some coaching institute?
I mean, this was actually from a text, no, textbook, but I don't know whether it will be that much genuine textbook. But there was another question, like it was actually from the gate question, like which one is having the largest shrinkage allowance while making a pattern for casting, and they are given options like aluminium, brass, cast iron, and plain carbon steel.
Okay.
uh, and they have given the solution as brass, and the reason that they given is the brass is having the highest coefficient of thermal expansion, so they are giving it as the highest shrinkage allowance.
Okay, so
The
like
doubt is actually in some books they have given.
see, I am not certain about this, the second question that you said, because this requires entirely numerical knowledge. Like you have to remember which material has higher shrinkage, and that kind of numerical knowledge I don't have at present. Like it is not something that I have in memory. So if they have considered that the shrinkage allowance of brass is maximum, then it will be like I cannot give an I cannot give you the answer that it is not that, because I don't know what is the shrinkage allowance for aluminum and what is the shrinkage allowance for brass. It is like you have to keep these numbers in memory, so it's difficult. So like, but other things other than that,
Okay.
the what I can say, the questions that you were asking related to the casting, like the solid shrinkage and allowance. So regarding that, what I can say is in mm, just give me a minute. Just give me a minute. Yes. So as I was saying, so the bronze, it has a shrinkage allowance of around 0.02. And what are the other materials they have given? Hello, am I audible?
Yes, sir.
Yeah, so you were talking about bronze and aluminum, right? And what other metals?
Yes, sir. Brass and aluminum and plain carbon steel
Uh, so see, carbon steel has
and
0.0,
cast iron.
0, plain carbon steel has around 0.02, aluminum has 0.013. What other thing you said? White cast iron, right?
In that P.N. Rao book, actually, when they have actually given a table for the, they only just said it is shrinkage 11, so we can consider it as solid shrinkage. They only said they have given a table like for different metals and a shrinkage. They have given like shrinkage 11. So if it is termed as shrinkage 11, then we can consider it as total shrinkage or only the pattern shrinkage. I mean
See,
the
shrinkage
we
allowance
have given
is
to S2
shrink.
room
See,
temperature.
let me first clear it out. Shrinkage allowance is always solid to solid shrinkage, as per my knowledge. Okay, and as per this course, that is Professor whatever he has taught in the class, solid to solid shrinkage, that is after the solidification happens, that shrinkage is called that is the solid to solid shrinkage is being taken care of by shrinkage allowance, and that shrinkage allowance is the only given on the pattern.
Okay, sir.
Okay, so what you were saying is that they have said shrinkage allowance. So shrinkage allowance is always considering only solid to solid, that is from the solidification, that is from the melting temperature when it has solidified till the room temperature, that is being taken care of by the shrinkage allowance, which is provided on the pattern. So any mention about the pattern allowance related to solidification and or the shrinkage allowance is always related to solid, that is solid at melting temperature to solid at the room temperature. Okay.
Okay, sir.
Okay, so should I start today's discussion now?
Yes, sir.
Okay, so
Yes, sir.
we will try to move a bit fast because we have already lost quite a amount of time. So just let me start. Okay, so I hope that the screen is visible and I am audible as well.
Yes, sir.
Okay, so
Yes, sir.
the nose in the temperature transformation time temperature transformation diagram refers to which of these? Can you give me the answer? The nose in the temperature time transformation diagram refers to which of these? Okay, so let me go through. So the solution is such that at the nose of the temperature diagram, uh, it is the minimum cooling rate required for conversion to martensite only. Okay, so suppose this is the TTT diagram that we are considering. Okay, and these are the conversion lines. Then this will be the nose, and any cooling rate which is higher than this, see, this is the time, so lesser is the time, lesser is the time, then faster is the cooling rate. So this is the minimum cooling rate. This is the minimum cooling rate required for conversion to martensite only. Okay, so this is the answer is option number D. So is it clear to you?
Yes, sir.
Yeah. So the answer is option number D. Is the minimum cooling rate. So like if the cooling rate is faster than this, then only conversion to martensite only will be possible. If the cooling rate is slower than this, that is the lines are like this. Okay, the lines sorry, mm, uh, the lines are in this region, the lines are in this region, then it will not form only martensite. It will form a mixture of either perlite plus martensite or bainite and martensite, depending on which region it is being cooled from. Okay, so for only martensite, it is the minimum.
So if it is more than, so the if the rate is very higher, then we will miss the nose and we move downwards.
See, if it is very high, like this,
The
yeah, like this, if it is the cooling rate, it is very high. Okay, then we will form directly martensite. This is the martensite. This is a perlite region. This is a bainite region. If this is how the cooling happens, then it will form to form perlite. If this is how it happens, then it will probably form bainite and then martensite. But for only martensite, this is a nose. So any cooling rate faster than this will result in the formation of only martensite. Okay.
okay, sir.
Okay. Then the next question: full annealing is not performed on hyperhutectoid steels because of which of the reasons? Is the answer known to you? Okay. So see, for hyperhutectoid steels, if full annealing is done, then very thick layers of Fe3C, that is cementite, is formed. Okay, and the structure will be the so in so the structure is basically perlite plus Fe3C, right? That is per some amount of perlite, then the remaining is Fe3C. But if full annealing is done, then Fe3C layers will be very thick. Okay, so in this structure, during machining, when the tools will strike these thick layers of Fe3C, they will undergo shock. That is called shock loading. That is why hyperutector steels are not subjected to full annealing. Okay, as a final heat treatment, they can be subjected to full annealing, but then some other heat treatment is to be performed so that the Fe3C layers, which have become very thick, can be their thickness can be reduced. Okay, but they cannot be performed as a final processing technique, or the final process. Okay, during machining, uh, results in in during machining there is shock loading of tools. So they are not subjected to full annealing as final treatment. Okay, they can be performed before but not as the final treatment. So the reason is to prevent the shock loading on tools. Answer B. Okay, so the next question, the process annealing is done to increase hardness, to relieve residual stress, reduce the effect of strain hardening or refining grain structure. So there are different kinds of annealing. One is full annealing, that is complete annealing that we discussed now. Then there is spheroidizing, in which spherical structures of this AP3C is formed in a pearl-like matrix. Then there is process annealing, and then there is stress relieving. Okay, so in stress relieving, it is the material is heated just below the lower critical temperature, so that there is softening and the residual stresses are released. Okay, and in process annealing, what is the main aim of the process annealing? It is heated below the lower critical temperature to reduce the effect of strain hardening. That is, if the surface has become strain hardened or work hardened, then to reduce that effect, that is to relieve that residual compressive stress, say residual compressive stress, to relieve that, it is done. That is to reduce the effect of strain hardening. Okay, so the process annealing is done to reduce the effect of strain hardening. Okay, and stress relieving is done to relieve the residual stresses. Okay, so I hope these two are clear to you.
So it is relieving the residual stress, or the option C is actually the reducing the effect of strain hardening.
Yeah, see,
Because it is also
residual
due to the
stress
strain
can
hardening,
be
isn't it?
tensile residual stress or compressive residual stress, anything. Like it is happening due to the say
So the
the
more correct answer will be the option B.
sorry.
I mean, is the option correct? Option C correct? I mean, if it is a multiple correct option, then can we pick that option C also?
Uh, that depends. Like in multiple correct options, relieving residual stress is not actually the main aim, because the tensile residual stress cannot be reduced, or mainly we refer to the residual stresses as those which are generated during the expansion and contraction during the heating process. Okay, so those are not relieved. If we are deforming during strain hardening, we are deforming the surface, or strain hardening, it is subjected to some kind of deformation, localized deformation, which is resulting in some localized stress, localized strains, which result in, although they result in some stresses, but that plastic strain which is remaining due to that deformation is what we are relieving. So if given a multiple choice question, I don't think that relieving residual stress is will be a correct answer for this, because we already have another type of annealing, that is stress relieving, for relieving the residual stress. Okay.
Okay, sir.
Okay. So in quenching process, just let me frame the question. I think this there is some like to know. Okay. So in quenching process, which of these is formed? So what is the main product of the quenching process? So can you tell me what is the main product
So
of the?
Banate and Martensite.
Not really. Only martensite.
So Banate and Martensite both. Banate, some of the Banate and uh, Martensite will be also formed.
See, quenching process, this whatever you are referring is the normalizing process, that in where bainite and martensite are both formed. In quenching process refers to a very rapid cooling process which is done like beyond the nose. That is, if this is the nose, then the cooling rate will be this. So this is quenching, and if it goes like this, then it is normalizing. Okay, so in normalizing, bainite and martensite can form, but in quenching process, only martensite will be formed. Okay.
Okay, sir.
And essentially in the you have to remember that in the quenching process, the cooling rate is greater than the critical cooling rate, which is defined by the nose. In the definition of the nose, we define that that is a minimum cooling rate required, right? So beyond that, the nose determines the minimum cooling rate. So in quenching, the cooling rate will be greater than that critical cooling rate. So only martensite will be formed in this process. Now this question in flow section hardening. Tensile stress is generated on the surface and compressive stress at the center. Or tensile stress is generated at the center and compressive stress on the surface. Or tensile stress is generated throughout or compressive stress is generated throughout. So do you know the answer to this? Okay, see what is true hardening. See, generally if we are hardening only the surface, then only the surface is considered. Now in true hardening, the entire till the entire depth of the material will be hardened throughout, from the surface to the center. Okay, so at the surface, when we are cooling it, this region will form martensite first, because this is subjected to the cooling fluid or whatever we are using as a cooling medium first. So martensite is formed. So martensite, when we are suppose we are forming this martensite from austenite, it is forming. Okay, we are decreasing the temperature. Then as martensite forms, martensite has a higher specific volume. This higher specific volume, that is the volume for a unit mass, is increasing. So since the volume is increasing, so it will try to stretch out the regions. Due to this, on the surface there will be tensile stress generated. Okay, and since this is stretching out, so the inner region will feel a compression from the outer region, that is from the surface region. So the inner region will have a compressive stress developed. Okay, so due in true hardening, true section, that is throughout, if we are hardening, then the tensile stress will be generated at the surface and compressive stress will be generated at the center. Okay, the reverse is the case for shallow, that is if we are hardening only the surface. Okay, if we are hardening only the surface, then in the bulk there is no increase or decrease in the volume due to this martensite formation, because only the surface is forming. Okay, so in that case only there will be compressive stress on the surface, and as a result tensile stress on the center. That is the opposite of this. Okay, so coming to the next problem.
Okay, sir.
During continuous cooling at just less than the critical cooling rate till 50% transformation line followed by rapid cooling results in which of these? So you have to know the continuous cooling diagram for this. So suppose this is time, this is temperature. Okay, and suppose these are the two transformation lines. It is said that transformation line. So till 50% transformation line, we are transforming it. Then what will be the structure formed? Can you tell me? See, it states that it is just less than a critical cooling line. So the critical cooling line is this. Just less than this will be something like this. Continuous cooling till the 50% transformation. If it is much lesser than the critical cooling line, then would have gone in this direction, but it is not so. So we will have to take just less than the critical cooling line. So perlite will not be formed. Bainite will be formed partially, 50% bainite, and then there is rapid cooling, which will result in the formation of martensite. So bainite and martensite will be formed in this case. Okay, so the answer will be C. Is it clear to you?
So, but actually, it is going out of the curve, isn't it? For the first bottom diagram, it will be. It also missed that nose, isn't it? So the martenite will be formed, and for the top line, even if we enter into that two curves, then that means the bayonet will be forming.
See, this is not the process. This is, I have just shown to show that this is a critical cooling rate. Okay. This is not the process. This is the process. This is the process. We start from here. It is just less than the critical cooling rate. So since it is just less than the critical cooling rate, so we have to take a line which is close to this nose. Okay, the cooling rate which is close to this nose. So we are taking this line. Okay. So in this line, in this region, there will be transformation from austenite to bainite, 50% bainite. The remaining austenite, when it reaches the 50% line, then there is a rapid cooling which will result in the formation of martensite. Okay. If it happens such that it is not just less, it is say much lesser than the critical cooling rate, then we have to take a line like this. That is till 50% perlite. Okay. This is the region where perlite is formed. That's what I meant by just less than the critical cooling rate. So, yeah, did you understand what I tried to say?
So if that time is given, then how we will be understanding it? I mean, in some question they are giving like it will be waiting 10 seconds or 20
Then you
seconds.
will have to know the for that particular composition. You will have to know the CCT diagram. Okay. Otherwise, you cannot know that till what time you will.
Okay, sir.
Yeah. So you will have to know the time ranges here. Okay, so for this nose, there will be a particular time here, right? So you will have to know that time. Otherwise, you won't be able to decide. Okay. Okay. Now another question: cooling rate greater than the critical cooling rate during heat treatment of the carbon steel results in which of these? Bainite, cementite, perlite, or martensite? We have already discussed this. You know the answer to this, right? If it is greater than the cooling critical cooling rate, what will happen?
So it will be martenite.
Yes, it will be martensite. Yeah. Now, next question: to improve the surface hardness in using induction hardening, thin layer of steel is heated up to which of these? You know the surface hardness and induction hardening process.
So I have just condition with that induction part. I covered that uh, nitriding carburizing those portions.
Okay, okay. So, just
So I think it will be oceanic range if it will be temperature is reaching 900 above. Uh,
Just
it,
a minute. I will do that. Just a minute.
so your voice is actually blurring. I mean, some noise out.
Yeah, I am sorry. Actually, the internet connection is a bit, I mean, not great today. So I think so that might be the issue. I hope it is. Is it better now? Hello, am I audible? Hello, am I audible?
Yes, sir.
Yeah, yeah. So is it better now? Is it better now?
Yes, sir.
Okay, so yeah,
It's audible.
so induction hardening, the thin layer of the steel is heated up to, yeah, it is right. We have to heat till the austenitic stage to form a homogeneous austenitic layer. That is homogeneous austenitic structure. So the answer is C. Okay, now the next problem. Yeah, so we have to match this processes. So can you tell me? Can you tell with me? So annealing is used for which of these?
So in the case of normalizing, it
No,
will be
no. Yeah, normalizing. Tell me.
relieving the stress. Normalizing will be like relieving the stress, and annealing will be the tempering will be refining the grain size.
See, first you
Nitriding
have
will
to
be surface
decide what you
hardening.
already know. Uh, just a minute. Put it back. Yeah. So
Nitriding
see,
will be surface hardening, and tempering will be refining grain size.
see, nitriding we know it will be surface hardening, right? Nitriding is surface hardening, right?
Yes, sir.
And martempering is
Tempering is
used for hard and brittle structure, right?
yes, sir.
Then we know this too. See, annealing has annealing. There are different kinds of annealing, and of that there is something called stress relieving, right? We have already discussed about annealing, stabilizing, stress relieving, and what was the other one that we discussed? That process annealing that reduce the strain hardening effect. So annealing is directly related to relieving the stress, and normalizing is related to defining the grain size. Okay, it is done in such a way so that in the bainite stage, suppose in the bainite stage, if you are forming bainite or pearlite stage such that very faster cooling rate forming pearlite or bainite in such a way that very fine grain structure is formed, then the hardness will also be increased, but the decrease in the ductility associated with the martens that is the formation of martensite will be less. That is, the decrease in the ductility or the toughness will be less, but there will be some increase, that is quite a significant increase in the hardness, that is related to the normalizing, that is refining the grain size. Okay, so the correct option will be A. B with 3, C with 4, and D with 1. Okay. Clear to you? Is it clear to you?
Yes, sir.
Okay. Now, reduction of brittleness. See, that's what I was talking about. Reduction in brittleness without any significant loss of hardness of martensitic steel can be achieved by which of these? See, if we form directly from austenite, then the reduction in the brittleness without any significant loss of hardness can be achieved by normalizing. But it said that without any significant loss of hardness of martensitic steel, that is, the martensitic steel has already formed. Now, if we want to reduce the brittleness without any significant loss of hardness, then what we have to do? We have to do the process of tempering. That is, we have to keep the martensitic steel that is formed to an elevated temperature for a longer duration of time, so that the grain growth can be possible, or not. If the grain growth is if the grain growth is not possible, if we don't take it to the till the grain growth region, then if we keep it below the temperature at which any grain growth is possible, then this martensitic steel uh, uh, sorry, let me just repeat, it got confused. See, if we are trying to reduce the brittleness by refining the grain structure, then we have to take the process of normalizing, where will we have to heat to the austenitic stage and then cool in such a way that pearlite or bainite structure is formed. But for martensite, if we have to reduce the brittleness, then we will have to keep it at an elevated temperature for a longer duration of time, such that the carbon in the lattice structure of martensite, it diffuses out. Okay, that will result in the reduction of brittleness. Okay, that is how we will achieve the reduction in brittleness without any significant loss in hardness. Okay.
Okay, sir.
So, do you know how martensite is formed? It is a diffusionless transformation of carbon, diffusionless transformation in which a BCC structure, that is body centered structure of carbon and iron, gets transformed to body centered tetragonal structure. It is because of this increase in the volume is that we get martensitic structure, hard martensitic structure. It is a diffusionless transformation. Now, if we subject it at a high temperature for a significant duration of time, then this carbon in the from the BCT structure will start gradually diffusing out, which will result in the reduction of brittleness. Okay, so the process is tempering.
Okay, sir.
So tempering of martensite releases carbon. Okay, releases carbon to form tempered martensite. This is called tempered martensite. Okay. Now coming to the next question, the process which helps to induce compressive residual stress on the surface of the metal is which of these? I think this is very common. You can answer this.
So short meaning.
Yes, short pinning is the correct answer. So the next question, the minimum bonding strength required for good survival of coating is? This is just a numerical data. I do. So do you know this value?
No, sir.
So see, the coating is attached to the surface, right? So coating is attached to the surface of the substrate, so that it remains attached. The coating should have a minimum strength of 70 MPa. That is like a empirical value, you can say that it has been taken that if the coating strength is 70 MPa or beyond that, then the coating will have a good strength enough to hold itself with the surface. Okay.
Okay, sir.
Yeah. So Yeah, so it is 70 MPa. Now, next question. The maximum hardness of low carbon steel can be achieved by which of the process? See, the low carbon steel we are considering here. Okay. So the maximum hardness of low carbon steel can be achieved by which of these?
So night trading.
Yeah. Why can we not achieve the hardness by, say, martempering, that is the formation of martensite?
So actually, for when we are doing the tempering, the wall structure will be hardened and brittle. But we can during this kind of surface treatment, only the surface level will be
But
hardened. Means
it has
from
not.
1 mm to 2 mm.
It has.
Night trading, we can. I think
What I'm saying is that nothing has been mentioned that we have to harden only the surface and not the bulk. So why cannot this martempering be used? It is not because it is only hardening the surface. Nitriding is only hardening the surface or something like that. There is another reason for it.
so. Is it the carbon content or anything?
Yes, it is a carbon content. See, in low carbon steel, for martensite transformation, see, martensite transformation will result in a higher hardness when a greater fraction of carbons, as I already said, right, it is due to the diffusionless transformation of BCC to BCT structure. So, the more the carbon atoms, the more will be like, more carbon atoms will now be in a position where they should not be. That is where the hardness is actually increasing. So if the carbon atoms, the quantity of carbon atoms itself is less, then even if there is a transformation from BCC to BCT, the carbon atoms are not there to fill up that. That is, they forcefully fill up that BCT structure. Then how will the hardness increase? So for low carbon steels, martensite, the formation of martensite by, say, martempering or austempering, all of these processes will not mm, uh, be beneficial enough for low carbon steels. For low carbon steels, we can achieve the hardness by these processes, that is adding of compounds. Since why add compounds? Because carbon is deficient here, right? So we have to add external compounds. So we can add carbon or extra carbon or nitrogen or a mixture of carbon and nitrogen. So it is either carbonitriding or nitriding or carbonizing. So of these, it has been observed that nitriding has the maximum hardness giving capacity in this for low carbon steel. So the correct option will be nitriding. So if asked why not martempering, don't say that it is on the surface or the bulk. It is because the carbon content is low. So marten formation of martensite will not give that much of high hardness. Okay.
Okay, sir. So, by meaning only the low carbon steel, will it contain any percentage of aluminium? Uh, Anything? I mean, for the night trading, we need some percentage of aluminium, isn't it, for formation of that precipitate?
Why aluminium you were saying for the precipitate? Nitrogen you were saying that for nitriding, nitrogen will have some compound formation with aluminium. I don't think it is such. Both low carbon steel and
Actually,
aluminium alloys.
I've read from a Groover textbook. They are giving.
It might be the case. I am not certain about it, but both low carbon steels and aluminium alloys can be subjected to maximum hardness using nitriding process. Okay, because aluminium steels, when there is, suppose in aluminium alloys, if as they have no or very less carbon, so they cannot be subjected to such heat treatment processes like mar tempering or os tempering. So in that case their hardness can be also be increased by processes like nitriding and carbonizing. So that's what I meant, that low carbon steel and aluminum alloys both can be hardened using nitriding process. But I am not certain if nitrogen reacts with aluminum, because I don't know that if nitrogen reacts with aluminum to form any particular component that will result in the formation of that will increase the hardness. So like if they have mentioned that in blue word, it might be the case. Anyway, so
Actually,
yeah.
the statement was like, to be most effective, the steel must contain certain alloying ingredients such as aluminium 0.85% or and chromium 5% or more.
Yeah, that's what I'm saying. That for more effective, see these they not necessarily form the compounds, but they form interstitial compounds, or they might form precipitation hardening in some cases. Is it particularly in case of low carbon steels, or in case of say mm, uh, nickel alloys also? In nickel alloys like inconel and all, they undergo precipitation hardening. So these compounds like the added compounds of chromium, molybdenum and all these, they form precipitates. That is a totally different range of hardening again, not related to nitriding, carbonizing or anything. That is a totally, that is, they form precipitates in the matrix. That is why the hardness is formed. So you just clear it out once again if they are talking about precipitation hardening or this nitriding carbonizing process of hardening.
So actually, they are talking about the night trading, but they have specified like for alloy steel.
For alloy what steels?
The surface night trading is a, I mean,
For
the night trading is a treatment in which nitrogen is diffused into surface of special alloy steel to
huh?
produce thin hard casting.
Hmm. So in that what they
So
have mentioned, that they it should contain chromium and aluminium for better effectiveness. Yeah, so the presence of
then
these compounds might
yes, yes.
affect, but that is not essentially the nitriding process. That even if aluminum is not present, then also the nitriding process will be successful. They might result in an
Okay,
improvement,
sir.
further improvement in
So
hardness, but that is
for
not
these four
essential.
processes, we can
Yeah, sorry,
so, if it for these four processes
your voice is not audible actually.
for all these three processes, we can say we can use a low carbon steel.
Yeah, low carbon steel, aluminum alloys also you can use. Okay, and particularly even medium carbon steels also you can use if you are only trying to harden the surface, as we are, these are surface treatment processes, right? Nitriding, carbonitriding and carbonizing, all of these are surface treatment processes. So if in os tempering or mar tempering, if we are not they will be changing the properties mostly to the bulk. So if the bulk properties are not able to meet surface changing properties, but we can use these processes. There is no restriction that only low carbon steel will be utilizing this process, but for low carbon steels this is the process. Okay.
Okay, sir.
Yeah, so now another question: to improve the surface hardness using nitriding, the steel is heated up to which of these state?
Sir, austerity.
No, this is done. See, that is a specific process specific condition. For nitriding, the temperature needs to be in the range of around 500 to 550 degrees. Okay, so this is heated up to the ferritic stage. If we heat up to the austenitic stage, then these what we can say, that we don't need to heat up to the austenitic state for the diffusion of nitrogen atoms into the surface. We this the reaction is better, that is this is actually, the nitriding is actually carried out in a ammonia environment where the ammonia is broken to nitrogen and hydrogen, and this reaction basically occurs in the range of 500 to 550 degrees. So the steel here is heated to the ferritic stage of 500 to 550 degrees to facilitate this process, the conversion process of ammonia to nitrogen and hydrogen, and the diffusion of nitrogen to the surface. So remember this, that for nitriding the heating is done till the ferritic stage. Okay.
Okay, sir.
Okay.
So for the carburizing, is it for till the austenitic?
Yeah, so yeah, carbonizing, it is done till 850 to 950 degrees Celsius. You have to hold it to 850 and 950 degrees Celsius. You have to hold it at that temperature to form homogeneous austenite, and then you will have to decrease it, the temperature. Okay. So for carbonizing, it is till austenitic stage, but for nitriding, it is till ferritic stage. Okay.
Okay, sir. So by meaning the martensitic stage, which temperature they are meaning? I mean, the formation of that martensite start, is it they are meaning
Yeah,
that? Or
martensitic start, martensitic, the temperature at which the martensitic formation starts.
so it will be very lower, isn't it?
It depends on the composition, but it won't be like very low. Like it depends on the composition. Like what do you mean by very low? Like what is very low temperature? Like minus you are considering?
I mean the no, I mean the
It is
current
generally about
uh,
200. It is generally
current
below
supply.
200 degrees. Okay. It is generally below 200 degrees.
Okay, sir.
Okay, but not like a negative temperature. Not that. Okay. Yeah. So
Okay, sir. So
the
by meaning the delta, is there any process that carried out in the delta region?
in the delta ferritic stage, not these heat treatment processes are not generally carried out, because by austenitic phase we reached a homogeneous phase. So, not, I don't think that there is any such treatment process which occurs beyond that.
Okay, sir.
Yeah. So the chromium coating in hot dipping process improves which of these? So what is the main function of chromium coating?
So corrosion,
Yes. So the chromium, the main
corrosion.
function is corrosion resistance. Okay. So chromium coating is done for B, corrosion resistance. Okay. So yeah. Now coming to the next question. In steels containing carbides of vanadium, tungsten, chromium, with increase in temperature of the tempering, the hardness increases or hardness decreases, hardness increases then decreases, or hardness decreases and increases. So can you give me the answer to this?
Uh, so the tempering is done to decrease the hardness, so could be decreasing the hardness.
Yeah, so that is hmm, that is C for, but it refers to steels which contain these carbides. Okay, so what happens is, in general, what happens? Just give me a minute. Okay, so tempering is basically done to reduce the hardness, right? That we know. So tempering process such alloying elements. Suppose this is the hardness. Okay. And hardness and toughness both are increasing, both are shown here. And this is temperature. Okay, so the hardness with temperature will decrease like this, and the toughness will increase like this. So see, if we are generally, if we are trying to improve the hardness by a little bit decrease in the, if we are trying to improve the toughness by a little bit decrease in the hardness, then we can use this temperature range for the heat treatment process. Say this is around 200. Okay, as the tempering temperature is increased, the hardness decreases further and further. So if we are to improve the toughness a lot, we at the cost of decrease in the hardness, that is the hardness will decrease a lot in that case, then the temperature of tempering, this is called tempering temperature. Say this is around 800, so it will be very low hardness. But what happens when these steels contain carbides of, say, vanadium or tungsten or chromium? In that case, see this vanadium, tungsten, chromium, all of these form, and other is say molybdenum, form carbides at higher temperature. Okay. So during the tempering process, say carbon is diffusing out, which is resulting in the decrease in the hardness and the increase in the toughness. But at same time, at the higher temperature, if these compounds of vanadium, tungsten, or chromium or molybdenum, they are forming carbides again, then they will occupy those spaces and the hardness will increase once again after a certain temperature. So we will get a curve something like this for, you can say that, mm, what to refer this as, steel contain, say these are for steels containing uh, mm, or alloying elements, this carbide forming elements, you can say carbide forming elements. Okay, and this is normal steels. Okay, this is tempering temperature, and this is hardness and toughness. So we will see that for these cases, till a particular temperature, it will decrease, the hardness will decrease. After that, the hardness will again start increasing because of the formation of the carbides at this higher temperature. So this higher temperature, till this value of temperature, there will be a decrease in the hardness till this carbide starts forming. Once this carbide starts forming, the hardness will again increase. Okay, so this is the hardness. And similarly, toughness also, it will start increasing till this point, and then the toughness will almost be constant. Okay, so the correct option will be hardness decreases and then increases. So the answer is option number D. So if there is any doubt, you can ask.
So, so for you have drawn that for the second diagram, the toughness. There was a second diagram, isn't it? For that is on that's the diagram for the carbide forming or the top diagram.
Which one? This one? This one you are referring to?
Yes, sir. This one or
This is the
yes, sir.
hardness. This is the hardness. This is the hardness. The hardness will decrease, and then after a
Okay, sir.
particular temperature, it will start increasing. This is hardness, and the toughness will uh,
Okay, sir.
increase up to a particular
So we don't need to know learn the tempering temperature. I mean the minimum point. We don't need to
No, no,
know
no.
that.
That is like very dependent on what elements you are having, what fraction of elements you are having. So that is like a very ambiguous thing to know. That depends on a lot of factors. Okay, you just need to know the concept that's what happens. Okay.
Okay, sir.
Yeah. So coming to the next question, in quenching process, the martensite formation occurs by which of these?
So diffusionless transformation.
Yes, diffusionless transformation. So, in diffusionless transformation, in the previous this thing, once we have seen during tempering, there is a decrease in the martensite releases carbon. So, what happens is that here I would like to say that this diffusing carbon, mm, uh, this the carbon diffusing out interacts with the iron, okay, in the steel to form another compound. It is not Fe3C, it is called epsilon carbide. That is Fe2.4C. Okay, it has reduced lattice strain. Since the lattice strain is reducing as compared to when it was a BCT structure, that is why the this brittleness will decrease. Okay.
So this tempered martensite, there we will have that diffusion.
Not necessarily tempered martens. This is an empirical relation, you can say. Martensite, you cannot say that it will be like Fe3C is cementite. It is not martensite. Okay, so it is epsilon carbide will be some of the like entire carbon and carbon will not diffuse out, right? Some of the carbon will diffuse out. So in that sections, this compound will be formed. So you cannot say that the tempered martensite is having this composition. This epsilon carbide will be formed at certain specific locations where the composition will be Fe2.4C and there the lattice strain will be reduced. Okay.
Okay, sir. So for the quenching and martensite formation, we can say it will be a diffusionless transformation. Is there any transformation, martensitic transformation, which have the diffusion? I mean, if it the previous option like the tempered martensite, we can fully say it will be diffusionless.
No, no, no. The tempered martensite will be by the diffusion of carbons out of the air. So it is a diffusion based formation. Tempered martensite is formed by diffusion process only. Martensite is formed by diffusion less transformation. That's what I'm saying.
Okay, sir, and all other process will be diffusion, isn't
All
it?
other processes,
Uh,
as in
I
which
mean the
processes?
the normalizing, annealing.
Normalizing,
Uh,
annealing are all based on diffusion based processes. Quenching, that is which results in the formation of martensite only, will be a diffusionless process. Okay.
so in the case of us tempering, will there be any diffusion similar to that mark tempering?
See, in os tempering process, what do we do? In os tempering process, we basically heat it to above the martensite start temperature, right? So even if some of the you know some of the structure from BCC to BCT that transformation from BCC to BCT could not form because we stopped the heating before the martensite could start forming, and then we keep it at a constant temperature, right? Where it is homogenized to bainite. See, you have to observe these things, okay? Where there is a horizontal line or a relatively horizontal line like this, you can say that there is diffusion, because diffusion is a time dependent phenomenon. If the time is very less, then the diffusion is very less. That's what we mean by diffusionless transformation. If the cooling rate is very fast, then the time of this transformation is very less, right? So there is no time for diffusion. Diffusion has the order or units of this meter square per second. So it is a time based phenomenon. Depending on what time scale you are considering, we have to say that it is diffusion based or diffusion less transformation. Since for the formation of martensite it is very fast, so the diffusion cannot happen. That is why it is a diffusionless process. We just don't name it as diffusionless process just like that. It is because there is no time for diffusion to happen. If it is a horizontal line, that means there is sufficient time for the diffusion to happen, and homogenization has happened in this case. That is why if we can very like clearly say that there is a diffusion in this phenomenon.
Okay, sir.
So in quenching process, basically the martensite formation is by diffusionless transformation. Now coming to the next question, the final product in ostempering is what? We have already discussed this. What is the final product in
So ban
ostempering?
it.
Yeah, so the final product in ostempering is bainite. So before that, let me just give you an overview of the ostempering and martempering process so that it becomes clear. So what happens in ostempering is, suppose this is the temperature and this is the time. So we will heat to a region which is mm, just above the martensitic start temperature, and then we will keep it to form a homogenized bainite. Homogenized to bainite. Okay, so this is the ostempering process. In this process, there is uh, no major decrease in ductility, in hardness. Sorry. See, I say it right there that the hardness can be increased by two processes. One is this where we either normalize it or do the ostempering process such that the grain structure is refined. So that there is no much decrease in hardness here, but the ductility is improved. But if we form martensite, then the hardness is increased a lot, but the ductility is significantly low. Now coming to the process of martempering. So in martempering, you can say it is basically a stepped martensiting process, stepped formation of martensite. Okay. So in martempering, what happens? We do it in steps. Suppose this is the cooling curve, then this is the martensitic start line, and this is the martensitic finish line. Okay. And so in martempering, what we will do? This is ostempering process, and this is the martempering process. Okay, so in this case, what do we do? We cool it to just above the martensitic start temperature. Then we keep it not to cross the nose, but below that. We keep it such that a homogeneous structure is formed here. Then we again cool it, and then we again keep it in a homogeneous, like a constant temperature. So this is a constant temperature bath. You can say that these are constant temperature baths. These are constant temperature. Okay, and this is the time where the transformation will take place. There will be cooling till this point, then there will be homogenization at a constant temperature, then there is another cooling which will result in the formation of martensite at this temperature. This point must be lesser, this must be less than martensitic finish temperature, and then we keep it again constant. Okay, so this is like a stepped formation of martensite. Okay, so this basically reduces the severity of the quenching. So if we cool all of a sudden, then that severity is reduced by this step quenching process. Okay, and because of this reduction in the severity of quenching, the uniformity increases. Uniformity, we are increasing the uniformity here, right, in this zone. So uniformity increases and the residual stresses decreases. So that is the overview of the Martin-Pering process. So is it clear to you?
Yes, sir.
Okay. So now going to the next question. This is related to surface modification. So the thinnest layer in surface modification can be produced by which of these? Laser cladding, nitrating, ion implantation, or well surfacing. So do you know the answer to this?
Sir, is it night riding? It's actually till point zero 0.03, sir.
No, it is actually ion implantation,
Point
wherein
zero
we
two five
it
night
is
riding.
uh, mm, no, nitriding will be more than this. In ion implantation,
Okay, sir.
it will be giving the thinnest layers. So the thinnest layers are given in ion implantation. Ion implantation, and the thickest layers are formed by well surfacing. And all these nitriding, laser cladding, whatever are there, they are all in between well surfacing. So, now coming to the next question. The transformation hardening is applicable for which of these low carbon steel, aluminum steel, nickel alloys, and low carbon steel, aluminum alloys, nickel alloys, medium to high carbon steel. So for which of these transformation hardening is applicable?
Sir, medium or high carbon steel.
Why?
We need that carbon content so that it can.
Yes, yes. So we have already discussed that, right? So basically, if we see the carbon content with carbon content, okay, if we see the hardness, then even if we form the hardness of martensite formed, if we even if we say that, then also with low carbon content the hardness will be very less. Okay, so for low carbon steel or aluminum alloys or nickel alloys, they cannot undergo transformation hardening for the improvement of hardness using this process. So for only for medium and high carbon steels, the transformation hardening will result in a significant increase in the hardness. That is why transformation hardening is used for medium and high carbon steels. So it is generally the carbon content is greater than 0.3%. So transformation hardening is used for medium or high carbon steels and the carbon content is greater than 0.3%. Okay, okay, so it is C. Now coming to the next question, after carburizing, tempering is done such that which of this is the correct answer. So after carburizing, why is again tempering done? You see what happens in the carburizing process is,
So, in order to make some carbon distributed from the bulk, I mean, reduce some of the hardness.
carburizing, nitrating, all of these are surface processes. Why will we require to distribute it in bulk? That is not the correct answer. What happens is that when carbon is added to a say medium carbon to a low carbon steel for the improvement of hardness, the carbon will by default, see, the steel will by default have a particular crystal structure unless a BCT structure is formed where the carbon, the added carbon atoms from the carburizing process can occupy those places. That process is not done, till then the hardness will not improve. So after carburizing, only the carbon atoms will occupy say random places, they are not occupying the particular BCT lattice structures. Okay, they are not forming BCT lattice structures. So the hardness will not improve directly just by carburizing. Okay, so uh, what happens is that in carburizing process first, so it is basically a two-step process. This temperature and this time. So it is first heated to around 850 to 950 degrees Celsius, where homogeneous austenite is formed and then cooled. There, here carbon atoms will diffuse into the surface. Okay, the diffusion of carbon atoms will depend upon what time, till what time we have done the carburizing. So depth of carburizing is proportional to root over of the time, where T stands for carburizing time. Okay, now once the carbon has diffused, we have to keep it homogeneous. That is, this structure, whatever carbon is now, if we fix it at that time, then at that temperature, then the carbon at the surface that has diffused, that is the carbon that has diffused to the surface, will now get distributed only in the surface, not in the bulk. You remember this. Then it is heated. Then it is heated to the temperature, to the again to the homogeneous gamma state, that is 850 to 950 degrees Celsius. Then it is quenched. Then it is quenched to form martensite. Okay. Tempering. This is the tempering
Okay, sir.
process, and this is the quenching process. See, when we do this, since the carbon content is has increased only on the surface, so when we form the homogeneous austenite on the surface and then quench it, only the surface layers will be converted to martensite and result in the increase in the hardness. That is why after carburizing, we must do this tempering process so that martensite can be formed. So the correct answer is option number A. Okay, otherwise there will not be any increase in hardness. Is it clear to you?
Yes, sir.
Okay, so coming to the next question, uh, reclamation process refers to which of these? So what do you mean by reclamation?
So is it applying coating on damaged surface?
Yeah, it is a application of coating only, but what is the purpose of that?
So either the corrosion resistance or having a shiny surface.
Okay, just a minute, just a minute. No, this the correct option is ap- uh, uh, applying coating on the damaged surfaces. Okay, so just give me a minute. I will explain this.